I have been present in some of the work that we do as part of a large UK-wide project, which I lead. It's called ASAIL, which stands for Advanced Strategies for Accelerating Ions with Lasers. Effectively, the work we do is in trying to develop a new acceleration technique for protons, but also different type of ions, which is based on high-power lasers. So it's radically different from other acceleration techniques which have been discussed at this meeting or that are used in convention in proton therapy. And it is a technique which is still being developed. So certainly we are at a low TRL level at the moment, but it presents some possible aspects that might be of interest for future options, let's say, for different therapies. It's radically different, so it might lead to a very different way of doing the therapy with ions. Our work is in trying to develop techniques which might make the treatment cheaper in the future. Of course, it's a long-term proposition. It's not going to happen soon. And also, we are exploring opportunities that might make it different and might make it more interesting, let's say, for implementation on a broader scale. In particularly, using lasers, for example, we have recent results that show that we can efficiently accelerate not only protons, but also other ion species, carbon, for example. And as you will see, by, for example, looking at the stands here, there are several solutions of the market for protons, but not much is available in terms of carbon, which is even more expensive to implement. Therefore, that could be a niche that, for example, we could target with a different type of acceleration if we can develop it to the required standard. To accelerate particles with laser, in particular ions, which is the focus here, you need very powerful lasers. And there are different techniques through which the ions can be accelerated. Different mechanisms which are pursued by researchers worldwide. The most established, let's say, is called target normal sheet acceleration. Effectively, an accelerator is, the concept of an accelerator using laser is very simple. You just irradiate with high-power laser a thin foil of any material, really, but typically metallic. And of course, we are talking about pulse lasers. So these are electromagnetic radiation which travels in short pulses, let's say of duration picosecond or even less, femtosecond. And you focus it onto a target with some specialized optics, clearly, into spots of, say, micrometer radius or so. Therefore, you have an enormous concentration of energy in space and time at that point. You immediately ionize the target, so you can rip out electrons and ions from the target. And there are processes through which let's say, the energy of the laser is transferred very efficiently to the electrons in that case. So the electrons then are energetic enough to stream through the foil. They reach the rear of the foil, ionize the surface, establish a very strong electric field there. And this electric field accelerates almost instantaneously ions from the target. So all the process, let's say, take place on a picosecond or so. And the electric field, let's say, that you generated during this process are many orders of magnitude higher than what you can sustain in a conventional accelerator. The main reason is that, let's say, conventional accelerator accelerate particles using radio frequency fields, so electromagnetic wave. But this is done in vacuum inside some metallic vessels. And if you raise the amplitude of this field too much, you start breaking down the container somehow. In a plasma, you can raise your field as much as you want because the plasma is already broken down somehow. It's already matter reduced to its elemental components. There are other mechanisms which are currently being developed. Is a range of them. One which is very interesting is called radiation pressure acceleration. In that case, you irradiate similarly with a very powerful laser, a very thin foil, in this case on the scale of tens of nanometer. And under the right conditions, so if you control the parameters of the laser appropriately, you can actually just propel the irradiated portion of the target forward by the radiation pressure of the laser pulse. And this is very promising because you can accelerate not only ions present at the surface, but also the main component of the target. So, for example, if you radiate carbon foils, a carbon foil you can radiate very, very efficiently carbon, and so there is very much interest in this development for future therapeutical opportunity. To introduce other species into therapy. Like I was talking about carbon, but there is interest also in intermediate species like helium or lithium or so on. And one of the features of laser ion acceleration is that it's very flexible in the sense that with the same setup, you can accelerate different particles just by simply changing the target that you irradiate. Not only that, you can also irradiating a target, you can also produce X-rays, electrons. So there are a range of different options which could be also combined, because with a laser it's relatively easy to have several pulses arriving, let's say, in the same interaction environment from different angles, for example. So there are options also in terms of mixed field irradiation or new diagnostic opportunities, for example. Of course, it's all hypothetical at this stage, I should say. It will make sense to do it only if the cost is reasonable, of course. But there are some options for, some opportunities, I would say, for reducing the cost, even of a standard installation, because one of the nice feature of a say, hypothetical laser center for therapy would be that you could propagate imagine you have a multi-center for proton therapy. At the moment, the way it works is that you produce the ions from an accelerator, and then these are transported to the several treatment rooms. And you have, in this case, basically what you have to transport is a very rigid beam of high energy ions, which requires large magnets for steering and requires radiation protection, because these particles, when they are bent, radiate, of course. If you could do that with a laser, in principle, with the same laser system, you could service several treatment rooms by transporting the laser radiation close to the patient and producing the ions in the room itself. So that will certainly bring to some savings, because of course this building requires thick concrete to shield radiation. And also at the end of the system, at the moment, let's say the largest center use gantries, which are a big magnetic system used to steer the beam around the patient. With an optical driver, you could probably reduce significantly the size of these gantries, because as you know, laser can be carried around by mirrors, so part of these gantries could be optical. Again, I mean, it's still too early to think about this in too much detail, but there are still already design studies for gantries based on let's say, extrapolation of what the laser-driven ions could provide, which are interesting and show already a reduced size respect to what is done now. From here, one message that I get is that even beyond the biology, it seems like that there is need of some hard evidence from clinical treatment, and there is still some controversy about that. So it is not completely clear that everybody agrees that protons are better in every case, for all the cases that are being put forward. But I don't know about that. On the basics of the physical deposition, it should be better. So if it is not like that, it is interesting and needs to be explored.